Before I begin, let me just acknowledge my partners in crime, Dr. Hamid Ibrahimian from University of Nevada, Reno, and Farid Gahari, who is a research scientist at UCLA, who prepared most of this presentation, by the way, and I think he put excessive amount of animations, so apologies in advance for that. I'll begin by describing why I believe structural health monitoring is needed. I will describe what the current practice is, and then, in my humble opinion, what the ideal solution is, which is different than the current solution, which I believe is a magic combination of highly detailed models, which is commonly referred to as digital twins these days, with some high-powered inverse problem solution methods. And the particular one that we have been adopting or building our toolbox around with, which is a Bayesian framework. I will give some validation examples from real life, verification on a Golden Gate Bridge across the bay there, and some application examples from projects that we're currently working on, which is primarily focused on the so-called Sandwell Canyon Bridge. So just like us, structures need doctors because we age and they do too. And then, of course, there's permanent and cyclic loads that initiate some damage. There are environmental effects, temperature cycles, humidity changes, minor earthquakes. These will sometimes initiate small amounts of damage, and combinations of all these effects can escalate the damage to a level where the structure is going to be vulnerable structurally. We also have older structures that we need to revisit because maybe we have just recently understood the incorrect things that we have done in the past in our designs, and we really need to quantify their current vulnerabilities with our new understanding, so we need to go and instrument them and understand how they're behaving and monitor them. There may be also instances where the configuration or utilization of a particular infrastructure element changes a little bit. You may have designed a certain bridge for a certain amount of traffic load, and then maybe there's more traffic now, or you just discovered a new fault line near that bridge that you didn't think was there, things like that. And of course, on top of all of that, we have the earth, wind, and fire, plus human elements that can create problems for our structures. And for all those things, monitoring through sensors and processing of that data for making engineering decisions as well as financial decisions is necessary. We have, of course, a huge inventory of old infrastructure. When we look at bridges, there are nearly 60,000 structurally deficient bridges in the United States, according to the American Road and Transportation Builders Association. Some states are in worse shape than others, perhaps, but the combined cost of these repairs and renewals run into billions, hundreds of billions of dollars per year if we want to catch up. So many of the agencies who own these assets used to look at these maintenance efforts and monitoring, structural health monitoring, as an option that they would do or not do. They did not necessarily believe in it all that much, especially instrument-based rather than vision-based methods. And I think the agencies are currently thinking about this as a need. Structural health monitoring became a need in their portfolio. And I believe, given the increasing vulnerabilities and exposure, I think in the near future, and of course reduction in sensor costs as well as improvements in inverse problem solution methods, I think they will soon start viewing this as a necessity, structural health monitoring as a necessity. So inventories of complex structures and infrastructure are exponentially growing. In maybe some of the Western developed countries, the growth is not necessarily exponential, but there are many countries in the world that are building like crazy. And then the design philosophies have been changing from just doing life safety and collapse prevention to business continuity, which means the performance requirements are increasing. And to be able to meet those things, we need to really monitor the structures more closely to see whether they're degrading or they're meeting their performance criteria. And losses and closures will cause indirect costs, and we are, through our regional assessment methodologies, all the talks that we have listened to yesterday and today, we know that the indirect costs are immense, And maybe we're just realizing or are able to quantify these indirect costs. And I think when we bring this information to the forefront, what the indirect costs are, maybe structural health monitoring is no longer going to look like a more expensive option that the agencies have shunned in the past. What is the current practice? The current practice is pretty much a periodic inspection that involves sending somebody there and looking at stuff. And as you can imagine, it's a time-consuming, labor-intensive, and obviously necessarily an expensive affair. And you can only inspect structures periodically, not continuously. So if something happens in between, you're going to miss that. And things can collapse, and that has happened. In Italy, it has happened. In Minnesota, it has happened. When you do visual inspections, often you have to close the bridge to traffic, so this is going to cause service interruptions. And last but not least, the assessment is typically subjective and prone to human errors. You can send to the same bridge 2 different people, experts, engineers. They may come back with different assessment results. And of course, you have the invisible damages. If there's a damage to a pile foundation after an earthquake, you may be able to get some evidence of that from a distance, from afar, by just looking at stuff. But you'll not be able to quantify it necessarily. If you have a tunnel lining that cracked, what does that mean? Does this mean that there's an imminent danger, or we can just kind of paint over? Now these will be things that periodic visual inspection is not able to catch. And as I was mentioning, things have collapsed in the past, and these assets were being monitored through the current practice, so things have fallen through the cracks, if you will. After a major event like an earthquake also, we have the job of assessing damage and prioritizing which structures and bridges need to be repaired, whether some asset needs to be closed for service, like a rail line. For example, in that Tohoku earthquake in Japan, Japanese Railways Association or Corporation had to inspect 1,400 different locations to be able to give a green light to the trains to begin. And if you don't have 1,400 people, expert engineers, that's going to take a long, long time. So a health monitoring system together with its method, not just the sensor system, but the software, should allow us to detect damage, whether there's damage or not, allow us to localize the damage. Where's the damage in all of this big system? Is it in the foundations? Is it there? Is it here? But most importantly, the ideal system should be able to allow us to quantify that damage, put numbers on the table. If there's a strength degradation, what is it? Is it 80% of the nominal, or is it 5% of the nominal? In the interest of time, I'm going to speed up a little bit, but there are many threads into this world of structural health monitoring. One of them is the sensor-based solutions. We have seen different sensors that people are trying to sort of synthesize. And in the sensor-based solutions, you put a sensor to a place where you think something is important or bad is going to happen, and then you just can continuously monitor that. Or you can just pick a place where you do a temporary closure, and then you do a test like radar tomography, ultrasonic testing, etc. And these are generally classified under the broad umbrella of so-called non-destructive evaluation. These again are expensive solutions. They will complement visual inspections, but they're not applicable at every location. They're not applicable continuously. You'll have to set up this test typically, and therefore you can cause performance or service interruptions. And typically the most important vulnerability of these non-destructive evaluation techniques is that they will not give you a system level insight. So if you don't have a model through which you can interpret these signals, you will not necessarily be able to come up with a good assessment of the structural health. And there's the other thread, which is the vibration-based structural health monitoring solutions. So you rely on some natural event like earthquake, wind, explosion. They don't have to be necessarily extreme event, but a large wind, etc. Or you can set up some sort of a shaking test, or you can just kind of listen to the structure under operational conditions. And the data that you're collecting, you can interpret through a different plethora of methods, some of which are useful, some of which have been sort of invented as mathematical curiosities that do not really apply to the real life. But you can interpret the data through different methods and then, do the job of detection, localization, and quantification. In this vibration-based structural health monitoring world, there are also different sub-threads. One of them is just look at the sensor data and look for anomalies. So you can employ artificial intelligence, machine learning, or just assess, or establish some threshold values to see if the sensor reading is off of that or something like that. The other one is the operational model analysis. And these two threads have severe vulnerabilities and very limited applicability in my humble opinion. The data mining approach, the data-driven approach is training data dependent. They're not really predictive. They have large and yet unquantified uncertainties. There's really, again, no system level insight. And it also requires dense sensor installation. That works in our human body. We're just organized in this way that we have nerves everywhere and a really big brain. We can't really replicate that in real world yet. So we cannot rely on these methods. Operational model analysis is also the method of choice in my research community, has been. But it is really also vulnerable because it has been based on very restrictive assumptions, which is the response is linear because you're doing modal analysis. You're solving an eigenvalue problem that assumes that the system is linear, but the system is often not linear, especially when it's damaged. And then most severe assumption is that the input that is exciting the structure is broadband white noise, and it never is, especially when there's a damaging event. If you have a high wind, that's a non-stationary, non-white noise, colored excitation. So if you're doing operational modal analysis to identify this or that, your results are all polluted by this mismatch of your model and method to the physical reality. So what are the attributes of a robust health monitoring rapid post-event assessment framework? Well, it should work for rapid post-event, meaning an earthquake happens, and if you have sensors on the ground, an adequately number of them, you should be able to process that data within minutes, maybe then hours, to be able to give an estimate of the losses, quantified losses in terms of losses or damage to the structural frames and other assets in a regional scale. And also, the same sensors should be able to address the long-term operational health and performance monitoring needs. It must be able to identify hidden and local damages. Also, it must be able to identify damages when they're small enough. If something is about to collapse, there's really no need to identify that anymore. A television crew will be there, somebody will tweet it, etc. And the more important part is the damage to the damage that is smaller, and then you have to make a choice, and the choice is more difficult to make, and so you need a quantified assessment. Also, a good health monitoring rapid post-event assessment framework should be self-improving, meaning the observations that you make over time should allow you to better understand and quantify the system. Meaning, if you have developed a digital twin of the asset and you're fine-tuning it, this tuning should get better and better as you accumulate more data. And anybody who's done work in this field understands that the behavior of any structure will change with seasons and day, the hour of the day, whether there's humidity, etc. So there's a baseline that is moving all the time. And if your damage signature is below that baseline, you can hardly ever classify that signal as a damage because that's just the baseline moving around. So if you don't have a system that adapts to uses all the accumulated data and understands the system better, it's not going to work out. So our approach has been, and we came to this little nook by making all the mistakes that I'm mentioning above. So it's just like a painful, but in the end, rewarding, I think, journey to learn from the mistakes. But now I think personally, and some other people would also join me in saying that we need to really use physics-based models. We should be able to consider nonlinear behavior, should be able to consider arbitrary input excitations that are non-stationary. we should be able to not only estimate the level of damage, but also provide our uncertainty of that estimate. You know, if I tell you there's the damage to the beam column connection, the strength is degraded by 15%, but my uncertainty is, you know, plus or minus 50%, that's probably not a good estimate, right? So I need to be able to say what my uncertainty is as well. And I should be able to also tell you through my observations what is the remaining life of this particular member. How many times has it been cycled to the design limit, towards the design limit to a certain threshold, so that I can do fatigue and life estimates. It has to be case specific, you know, it should be able to handle earthquakes, winds, etc., you know, and provide us with system level insight and allow us to identify the hidden damages. So this is just a list of the things that I have done with my group over the years and with some colleagues, but to get to where we are, it took us more than a decade of study and learning from other people. Right now, in a nutshell, we have a digital twin-based damage identification and health and performance monitoring system that can address different needs. We can do operational condition assessments. We can also do rapid post-event assessment. These are different modalities, and they require different sub-algorithms to handle. We can also do detailed post-event assessment, and we can also do scenario-based prediction and preparation using the updated digital model to see how it might behave on a particular type of future earthquake that hasn't happened yet. There's a lot of mini algorithms that are stitched together that is supporting the system, but this is the overarching algorithm, which is a Bayesian estimation theory. So you create a model, and the properties of that model are represented by a probability distribution function. And then you make observations and you update the probabilities, and your observation gets better and better. We've been able to apply it to large structures such as the Golden Gate Bridge in different modalities, where in Golden Gate Bridge there's no soil structure interaction. It's sitting on good rock. And we have sensors on the piers, so what we're measuring there is the pure input motion. In a soil structure interaction case, those will not be pure input motions, but we can use it in this input-output modality. There are other bridges like the Vincent Thomas Bridge where you don't have the full set of measurements, so you have only a partial knowledge of what the input excitations are. We can use it in that modality. And there are many other bridges where you have no idea what the input is, even if you have sensors in some foundation or pier system. Because of SSI, what you're measuring is not pure input, so you have to do it in the output-only modality. So we have done stuff like that. So over time, we have progressed from theoretical problems to real-life applications supported by many projects from our state agencies and some federal agencies. Some of these projects are ongoing. So here's a project that we carried out some years back for Caltrans, who were interested in the Samoa Channel Bridge in Eureka, Northern California. It's a water crossing bridge. And the superstructure is relatively simple. And what they were wondering was, what are the dynamic foundation stiffnesses of this water crossing bridge? It's on soft soil naturally. And there were many earthquakes recorded on this particular bridge. So we've applied, or rather we were using these projects to refine and hone our methods, and this was a sort of a seminal project for us. And we were able to create the so-called blind modal identification method with which you can handle these soil structure interaction problems that have nonlinearities. So we have used 6 or 7 past earthquakes to estimate the dynamic foundation stiffnesses, and then we submitted our report to Caltrans, and then another earthquake happened. And then we had to do a sort of a blind prediction. We have used our digital twin that was calibrated from prior earthquakes to blindly predict what happened in the 2014 Ferndale earthquake. And so these are the Class A blind predictions of what is recorded on the bridge during that earthquake and what the digital twin is predicting. This is a particularly difficult case, and there's a big report on that, but the particular difficulty lies in the fact that soil behaves non-linearly during that earthquake. So there's some soil softening which recovers after a while from the earthquake, but this is an application that kind of gave us a good momentum in our efforts. We've also applied our techniques or refined and honed our techniques with data from the CSMIP buildings, California Strong Motion Instrumentation Program buildings. This is the Millikan Library, the famous one. And it is also particularly prone to soil structure interaction because it is a very stiff shear wall and a relatively soft foundation. So we've created a digital twin of it and used past earthquakes to back calculate its frequency-dependent foundation impedance function, which itself is a challenge. And then we have used the calibrated digital twin together with its dynamic foundation model to predict what its behavior was in another earthquake. These are comparisons of recorded versus predicted measurements. We have packaged versions of our tools for processing seismic data. We have a version that works on different types of buildings, which sucks in the data from the storm motion instrumentation center. It processes it. It outputs an automated report. This is a layout of the report. It also helps you visualize the behavior, etc. We have also worked hard to make it work for large structures, large bridges. And we have created some workflows that allows us to basically create models of bridges, often from images alone. And then we have to stitch different modeling tools, for example, SAP 2000 or OpenSeas, which are wrapped inside our estimator, Bayesian estimator. So all of these things had to come together so that we could basically apply it to a large set of tools. We are also creating a version of it for bridges. I am going to just maybe go to one last example where we are working on a current project for FHWA. And this is for performance monitoring of ordinary bridges. Ordinary bridges will suffer damage, and the damage is only visible when you have a significant heavy traffic on it. From ambient vibrations, you cannot get this damage. And when the bridge is traversed by many vehicles, the excitation is non-stationary and they're not measured. You do not know precisely what weight that truck has, and there are multiple vehicles passing, etc. So you do not know the input, but this is the only kind of input that can help you get a signal of the damage. So we have devised our methodology that works on windows of data that not only estimates the damage, but also estimates the weight of the vehicles traversing the bridge. And for that, our algorithm was falling a little bit short, so we aided with cameras. The cameras are trained on the traffic, and they classify the vehicle based on the image, whether it's a light vehicle, heavy, etc. And then it also approximately determines their relative location from an abutment. And we use that information and refine the load estimate of that vehicle, of multiple vehicles, together with the delamination damage that the bridge has. This is a SBIR phase 2 project, so if we can convince, for example, Caltrans or other agencies, and we're doing some field tests to prove it, because we can do it on paper, then they may adopt it on whole scale, and so that'll open new avenues. So with that, I'll just yield the floor. Thank you.